carry on with this exact solution. So we've got to transform the boundary condition. So our equation is really simple for phi. We can solve that exactly. It's just the heat equation or the diffusion equation. So remember we had u of x comma 0 was equal to f of x. But we also had that u of x comma 0 was the time derivative of, make sure we get this right, sorry, the x derivative of psi, which is the x derivative of this log phi x derivative of minus 2 nu, to go and check that out, log phi. So we have f of x is equal to, if I take the derivative of that, I'm going to get minus 2 nu dx phi over phi. Alright, so it's actually, it's easiest to solve this by integration here, to try and solve for the phi, because we've got to solve this equation for phi. So we've got d by dx of minus 2 nu phi log of phi, sorry, is equal to f of x. So minus 2 nu log of phi is the integral from 0 to x of f of s ds. So we can rearrange that and get phi of x comma 0, the initial condition, is the exponential of 1 over 2 nu minus 1 over 2 nu integral from 0 to x of f of s ds. Okay, and we'll just give this a name here, this function. We'll call this big phi of x. So if we look at it, okay, forgetting for a second here that how we've got to do this integration here. Clear this off. What we've got to solve is dt phi is equal to nu dx squared phi, and phi of x comma 0 is phi of x. And we can solve this by taking the Fourier transform. So in Fourier space we get dt of phi hat is equal to minus k squared nu phi hat. So phi hat is equal to e to the minus k squared nu times t multiplied by big phi hat of k. The Fourier, okay, we're changing colours here. Big phi hat of k is the Fourier transform of phi of x. I think we've got to Fourier transform the initial condition. I should make this like a little squiggly f to make sure it's a Fourier transform. So we've got to Fourier transform the initial condition. So when we inverse Fourier transform, we get the convolution. So we know the inverse Fourier transform of that. So what is the inverse Fourier transform? I'm trying to write this as a fancy f. See if I can do that. Inverse Fourier transform, not terribly well, of e to the minus k squared nu t. This is the Fourier transform of a Gaussian. So it's going to be another Gaussian. So one of the properties of the Fourier transform is it transforms Gaussians to Gaussians. So you can just look this up. And it's e to the minus x squared over 4 nu t, and there'll be some sort of square root of pi or some funny normalization factor. I use these results a lot. There you go. So that's the inverse Fourier transform of that. That Gaussian in k becomes a Gaussian in x. Okay, and they scale, and they have interesting properties when you transform a Gaussian. So if you have a narrow or a pokey Gaussian, it'll transform to make a squidged out one. And if you have a squidged out one, it'll make a narrow one. And that's Heisenberg's uncertainty principle, essentially. That really is just what Heisenberg. It's one way of conceptualizing Heisenberg's uncertainty principle, I should say. It's a mathematical way of seeing it. Okay? So if you've got a localized electron, localized x, then you're going to have smeared out y, momentum, etc. Because the momentum and position are related by the Fourier transform. Okay, so then we know that when we inverse Fourier transform two functions like this, then we get the convolution of them. So we finally get this expression for phi of x, comma t, is the convolution of phi with this function here, whatever we call this thing here. If you necessarily want to write it out again. So that is the integral from minus infinity to infinity. Just to make sure I write it in the same way here. Phi of y. So this is just a constant, it just depends on the time. E to the power of minus, not x squared, but x minus y squared over 4 nu t dy. So there's the solution here to phi. So we can do a few tricks with this just to get ourselves into a slightly neater version of the solution. So we introduce this term, this function f of x yt, which is equal to 1 over 2 nu, the integral from 0 to y, f of s ds, so that's the initial condition, plus x minus y squared over 2t. And then we find the solution is phi of x comma t is 1 over 2 square root of pi nu t integral from minus infinity to infinity e to the power exponential of minus f over 2 nu dy. And then u is equal to minus 2 nu dx phi over phi, which is going to be equal to so the x derivative of this function here, this function f, when we take it through here, we're going to get x minus, the only place the x appears here is it doesn't appear in this term here. So we're going to get 2, divide cancel with the 2, we're going to get x minus y over t. So this whole expression becomes, and there's a bit of cancellation because this term here appears out the front of both of these, it's going to cancel. And you get the integral from minus infinity to infinity of x minus y over t exponential of divided by okay, there you go. Okay, so this is the derivative of this. We've taken the derivative of f. There's a bit of a cancellation here with the 2 n's and the 2 nu out the front here. Okay, amazing. And so this is the solution here, and you can compute it, and you do get an exact solution. It's not time stepping and all of that stuff. It's kind of amazing. This is about as complicated as exact solutions get, I think. And there are people who tend to, chase around after them, but it's really very rare to get something that's much more complicated than this, and it starts to become, difficult to implement it. This is perfectly calculable. You're going to have to do this integration numerically, especially with the fact that the phi here is given as an arbitrary function. So that concludes this lecture, and it concludes the entire course.